Chapter 16, Fearless Concurrency. Handling concurrent programming safely and effectively is another of Rust's major goals. Concurrent programming, where different parts of a program execute independently, and parallel programming, where different parts of a program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. Historically, programming in these contexts has been difficult and error-prone. Rust hopes to change that. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools that to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. Therefore, rather than making you spend lots of time trying to reproduce the exact circumstances under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. As a result, you can fix your code while you're working on it rather than potentially after it has been shipped to production. We've nicknamed this aspect of Rust Fearless Concurrency. Fearless concurrency allows you to write code that is free from subtle bugs and is easy to refactor without introducing new bugs. For simplicity's sake, we'll refer to many of the problems as concurrent rather than being more precise by saying concurrent and or parallel. If this book were about concurrency and or parallelism, we'd be more specific. For this chapter, please mentally substitute concurrent and or parallel whenever we use concurrent. Many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang has elegant functionality for message passing concurrency, but has only obscure ways to share state between threads. Supporting only a subset of possible solutions is a reasonable strategy for higher level languages, because a higher level language promises benefits from giving up some control to gain abstractions. However, low-level languages are expected to provide the solution with the best performance in any given situation and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. Here are the topics we'll cover in this chapter. How to create threads to run multiple pieces of code at the same time. Message passing concurrency, where channels send messages between threads. Shared state concurrency, where multiple threads have access to some piece of data. And the sync and send traits, which extend Rust concurrency guarantees to user-defined types as well as types provided by the standard library. Using threads to run code simultaneously. In most current operating systems, an, an executed program's code is run in a process, and the operating system manages multiple processes at once within your program. You can also have independent parts that run simultaneously. The features that run these independent parts are called threads. Splitting the compilation in your program into multiple threads can improve performance because the program does multiple tasks at the same time. But it also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order of which parts of your code on different threads will run. This can lead to problems such as race conditions, where threads are accessing data or resources in an inconsistent order, deadlocks, where two threads are waiting for each other to finish before using a resource the other thread has, preventing both threads from continuing, and bugs that happen only in certain situations and are hard to reproduce and fix reliably. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in programs running in a single thread. Programming languages implement threads in different ways. Many operating systems provide an API for creating new threads. This model, where a language calls the operating system APIs to create threads, is sometimes called one-to-one, meaning one operating system thread per one language thread. Many programming languages provide their own special implementation of threads. Programming language provided threads are known as green threads, and languages that use these green threads will execute them in the context of a different number of operating system threads. For this reason, the green threaded model is called the M to N model. There are M green threads per N operating system threads, where M and N are not necessarily the same number. Each model has its own advantages and trade-offs, and the trade-off most important to Rust is runtime support. Runtime is a confusing term and can have different meanings in different contexts. In this context, by runtime we mean code that is included by the language in every binary. This code can be large or small depending on the language, but every non-assembly language will have some amount of runtime code. For that reason, colloquially, when people say a language has no runtime, they often mean small runtime. Smaller runtimes have fewer features but have the advantage of resulting in smaller binaries, which makes them the easier to compile the language with the other language in more context. Although many languages are okay with increasing the runtime size in exchange for more features, Rust needs to have nearly no runtime and cannot compromise on being able to call into C to maintain performance. The green threading M to N model requires a large language runtime to manage threads. As such, the Rust standard library only provides an implementation of one-to-one threading because Rust is such a low-level language. There are crates that implement M-to-M threading if you would rather trade overhead for aspects such as more control over threads, run when, and lower cost of context switching, for example. Now that we've defined threads in Rust, let's explore how to use a thread-related API provided by the standard library. Creating a new thread with spawn. To create a new thread, we call the thread : spawn function and passes it a closure. We talked about closures in chapter 13, containing the code we want to run in the new thread. The example in listing 16-1 prints some text from the main thread and other text from a new thread. Listing 16-1, creating a new thread to print one thing while the other main thread prints something else. Note that with this function, the new thread will be stopped when the main thread ends. Whether or not it has finished running, the output from this program might be a little different every time, but it will look similar to the following. The calls to thread : sleep force a thread to stop its execution for a short duration, allowing a different thread to run. The threads will probably take turns, but that isn't guaranteed. It depends on how your operating system schedules the threads. In this run, the main thread printed first, even though the printed statement from the spawn thread appears first in the code. And even though we told the spawn thread to print until I is 9, it only got to 5 before the main thread shut down. If you run this code and only see output from the main thread or don't see any overlap, try increasing the numbers in the ranges to create more opportunities for the operating system to switch between threads. Waiting for all threads to finish using join handles. The code in listing 16-1 not only stops the spawn thread permanently, most of the time due to main thread ending, but also can guarantee that the spawn thread will get to run. But also can't guarantee that the spawn thread will get to run at all. The reason is that there's no guarantee on the order in which threads run. We can fix that problem of the spawn thread not getting to run or not getting to run completely by saving the return value of thread : spawn in a variable. The return type of thread : spawn is join handle. A join handle is an owned value that when we call the join method on it, will wait for its thread to finish. Listing 16-2 shows how to use the join handle of the thread we created in listing 16-1 and call join to make sure the spawned thread finishes before main exits. Listing 16-2, saving a join handle from thread : spawn to guarantee the thread is run to completion. Calling join on the handle block blocks the thread currently running until the thread represented by the handle terminates. Blocking a thread means that that thread is prevented from performing work or exiting because we put the call to join after the main thread's for loop. Running listing 16-2 should produce output similar to this. Two threads continue alternating, but the main thread waits because of the call to handle.join parentheses and does not end until the spawn thread is finished. But let's see what happens when we instead move handle.join parentheses before the for loop in the main, like this. The main thread will wait for the spawn thread to finish and then run its for loop. So the output won't be interleaved anymore as shown here. Small details such as where the join is called can affect whether or not your threads run at the same time. Using move closures with threads. The move closure is often used alongside thread : spawn because it allows you to use data from one thread in another thread. In chapter 13 we mentioned we can use the move keyword before the perimeter list in a closure to force the closure to take ownership of the values it uses in the environment. This technique is especially useful when creating new threads in order to transfer ownership of values from one thread to another. Notice in listing 16-1 that the closure we pass to thread : spawn takes no arguments. We are not using any data from the main thread in the spawn thread's code. To use data from the main thread in the spawn thread's closure must capture the values we need in listing 16-3, shows an attempt to create a vector in the main thread and uses it in the spawn thread. However, this won't work yet, as you'll see in a moment. Listing 16-3, attempting to use a vector created by the main thread in another thread. The closure uses v, so it will capture v and make it part of the closure's environment. Because thread : spawn runs this closure in a new thread, we should be able to access v inside that new thread. But when we compile this example, we get the following error. Rust infers how to capture v, and because print line ! Only needs a reference to v, that closure tries to borrow v. However, there's a problem. Rust can't tell how long the spawn thread will run, so it doesn't know if the reference to v will always be valid. Listing 16-4 provides a scenario that's more likely to have a reference to v that won't be valid. Listing 16-4, a thread with a closure that attempts to capture a reference to v from the main thread that drops v. If we were allowed to run this code, there's a possibility the spawn thread wouldn't be immediately put in the background without running at all. The spawn thread has a reference to v inside, but that main thread immediately drops v using the drop function we discussed in chapter 15. Then, when the spawn thread starts to execute, v is no longer valid, so the reference to it also invalid. Oh no. To fix the compiler error in listing 16-3, we can use the error message advice. By adding the move keyword before the closures, we can force the closure to take ownership of the values it's using rather than allowing Rust to infer that it should borrow the values. The modification to listing 16-3 shown in listing 16-5 will compile and run as we intend. Listing 16-5, using the move keyword to force a closure to take ownership of the value it uses. What would happen to the code in listing 16-4 where the main thread called drop if we use a move closure? Would move fix that case? Unfortunately, no. We would get a different error because what listing 16-4 is trying to do is not allowed for a different reason. If we add move to the closure, we would move V into the closure's environment, and we could no longer call drop on it in the main thread. We would get this compiler error instead. Rust's ownership rules have saved us again. We got an error from the code in listing 16-3 because Rust was being conservative and only borrowing V for the thread, which meant the main thread could theoretically invalidate the spawn thread's reference by telling Rust to move ownership of V to the spawn thread. We're guaranteeing Rust that the main thread won't use V anymore if we change listing 16-4 in the same way. We're then violating the ownership rules when we try to use V in the main thread. The move keyword overrides Rust's conservative default of borrowing. It doesn't let us violate the ownership rules. With a basic understanding of threads and the thread API, let's look at what we can do with threads. Using message passing to transfer data between threads. One increasingly popular approach to ensuring safe concurrency is message passing, where threads are actors communicating by sending each other messages containing data. Here's the idea in a slogan from the Go language documentation. Do not communicate by sharing memory. Instead, share memory by communicating. One major tool Rust has for accomplishing message sending concurrency is the channel, a programming concept that Rust standard library provides an implementation of. You can imagine a channel in a programming as being like a channel of water, such as stream or a river. If you put something like a rubber duck or a boat into a stream, it will travel downstream to the end of the waterway. The channel in programming has two halves, a transmitter and a receiver. The transmitter half is the upstream location where you put rubber ducks into the river, and the receiver half is where the rubber ducks end up downstream. One part of your code calls methods on the transmitter with the data you want to send, and another part checks the receiving end for the arrival message. A channel is said to be closed if either the transmitter or receiver half is dropped. Here we'll work up to a program that has one thread to generate values and send them down a channel, and another thread that will receive the values and print them out. We'll be sending simple values between threads using a channel to illustrate the feature. Once you're familiar with the technique, you could use channels to implement a chat system or a system where many threads perform parts of a calculation and send the parts to one thread that aggregates the result. First, in listing 16-6, we'll create a channel but not do anything with it. Note that this won't compile yet because Rust can't tell what type of value we want to send over the channel. Listing 16-6, creating a channel and assigning the two halves to TX and RX. Transmit and receive. We create a new channel using the MPSC : channel function. The MPSC stands for multiple producer, single consumer. In short, the Rust standard library implements channels means as channel can have multiple sending ends that produce values but only one receiving and that consumes those values. Imagine multiple streams flowing together into one big river. Everything is sent down. Any of the streams will end up in one river at the end. We'll start with a single producer for now, but we'll add multiple producers when we get this example working. The MPSC : channel function returns a tuple, the first element of which is the sending end and the second element is the receiving end. The abbreviation TX and RX are traditionally used in many fields for transmitter and receiver respectively, so we name our variables as such to indicate each end. We're using a let statement with a pattern that destructures the tuples. We'll discuss the use of patterns in let statements and destructuring in Chapter 18. Using a let statement this way is a convenient approach to extract the pieces of the tuple returned by MPSC : channel. Let's move the transmitting end into a spawning thread and have it send one string so the spawned thread is communicating with the main thread. As shown in listing 16-7, this is like putting a rubber duck in a river upstream or sending a chat message from one thread to another. Listing 16-7, moving TX to a spawn thread and sending hi. Again, we're using thread : spawn to create a new thread and then using move to move TX into the closure so the spawn thread owns TX. The spawn thread needs to own the transmitting end of the channel to be able to send messages through the channel. The transmitting end has a send method that takes the value we want to send. The send method returns a result TE type, so if the receiving end has already been dropped and there's nowhere to send a value, the send operation will return an error. In this example, we're calling unwrap to panic in a case of an error, but in a real application, we would handle it properly. Return to Chapter 9 to review strategies for proper error handling. In listing 16-8, we'll get the value from the receiving end of the channel in the main thread. This is like receiving the rubber duck from the water at the end of the river or like getting a chat message. Listing 16-8, receiving the value hi in the main thread and printing it. The receiving end of the channel has two useful methods: receive and try_receive. We're using receive, short for receive, which will block the main thread's execution and wait until the value is sent down the channel. Once the value is sent, receive will use it in result TE. When the sending end of the channel closes, receive will return an error to signal that no more values will be coming. The the try underscore receive method doesn't block, but will instead return a result TE immediately. An OK value holding a message if one is available, and an error value if there aren't any messages this time. Use try underscore receive is useful if the thread has other work to do while waiting for messages. We could write a loop that calls try underscore receive very so often. Handles a message if one is available and otherwise does other work for a little while until checking again. We've used receive in this example for simplicity. We don't have any other work for the main thread to do other than wait for messages, so blocking the main thread is appropriate. When we run the code in listing 16-8, we'll see the value printed from the main thread. Perfect. Channel and ownership transfer. The ownership rules play a vital role in message sending because they help you write safe concurrent code. Preventing errors in concurrent programming is the advantage of thinking about ownership through your Rust programs. Let's do an experiment to show how channels in ownership work together to prevent problems. We'll try to use a val value in the spawn thread after we send it down the channel. Try compiling a code in listing 16-9 to see why this code isn't allowed. Listing 16-9 attempting to use the val after value after we send it down the channel. Here we try to print val value after we've sent it down the channel via tx.send, transmit send. Allowing this would be a bad idea. Once the value has been sent to another thread, that thread could modify or drop it before we try to use the value again. Potentially, the other thread's modifications could cause errors or unexpected results due to inconsistent or non-existent data. However, Rust gives an error if we try to compile the code in listing 16-9. Our concurrency mistake has caused a compile time error. The send function takes ownership of the parameter, and when the value is moved, the receiver takes ownership of it. This stops us from accidentally using the value again after sending it. The ownership system checks that everything is okay. Sending multiple values and seeing the receiver waiting. The code in listing 16-8 compiled it and ran, but it didn't clearly show us the two separate threads we're talking to in each other over the channel. In listing 16-10, we've made some modifications that will prove the code in listing 16-8 is running concurrently. The spawn thread will now send multiple messages and pause for a second between each message. Listing 16-10, sending multiple messages and pausing between each. This time the spawn thread has a vector of strings that we want to send to the main thread. We iterate over them, sending each individually and pause between each by calling the thread : sleep function with a duration value of 1 second. In the main thread, we're not calling the receive function explicitly anymore. Instead, we're treating Rx as an iterator. For each value received, we're printing it, and then the channel is closed. Iteration will end. When running the code in listing 16-10, you should see the following output with 1 second pause in between each line. Because we don't have any code that pauses or delays in the for loop in the main thread, we can tell that the main thread is waiting to receive values from the spawned thread. Creating multiple producers by cloning the transmitter. Earlier we mentioned that MPSC was an acronym for multiple producer single consumer. Let's put MPSC to use and expand the code in listing 16-10 to create multiple threads that all send values to the same receiver. We can do this by cloning the transmitting half of the channel, as shown in listing 16-11. Sending multiple listing 16-11, sending multiple messages from multiple producers. This time, before we create the first spawn thread, we call clone on the sending end of the channel. This will give us a new sending handle we can pass to the first spawn thread. We pass the original sending end of the channel to the second spawned thread. This gives us two threads, each sending different messages to the receiving end of the channel. When you run the code, your output should look something like this. You might see the values in another order. It depends on your system. This is what makes concurrency interesting as well as difficult. If you experiment with thread : sleep, giving it various values in the different threads, each run will be more non-deterministic and create different output each time. Now that we've looked at how channels work, let's look at a different method of concurrency. Shared state concurrency. Message passing is a fine way of handling concurrency, but it's not the only one. Consider this part of the slogan from the Go language documentation again. Do not communicate by sharing memory. What would communicating by shared memory look like? In addition, why would messaging passing enthusiasts not use it do the opposite instead? In a way, channels in any programming language are similar to single ownership, because once you transfer a ownership down a channel, you should no longer use the value. Shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location at the same time, as you saw in Chapter 15. Where smart pointers made multiple ownerships possible, multiple ownership can add complexity because these different owners need managing. Rust type system and ownership rules greatly assist in getting this management correct. For example, let's look at mutexes. Okay, one of the more common concurrency primitives for shared memory. Using mutexes to allow access to data from one thread at a time. Mutex is an abbreviation for mutual exclusion, as in mutex allows only one thread to access some data at any given time. To access the data in mutex, A thread must first signal that it wants some access by asking to acquire the mutex lock. The lock is a data structure that is part of the mutex that keeps track of who currently has exclusive access to the data. Therefore, the mutex is described as guarding the data it holds via the locking system. Mutexes have a reputation for being difficult to use because you have to remember two rules. When you must attempt to acquire the lock before using the data. When you're done with the data that the mutex guards, you must unlock the data so other threads can acquire the lock. For a real-world metaphor for mutex, imagine a panel discussion at a conference with only one microphone. Before a panelist can speak, they have to ask or signal that they want to use the microphone. When they get the microphone, they can talk as long as they want and then hand the microphone to the next panelist who requests to speak. If a panelist forgets to hand the microphone off when they're finished with it, no one else is able to speak. If management of the shared microphone goes wrong, the panel won't work as planned. Management of mutex can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. However, thanks to Rust's type system and ownership rules, you can't get locking and unlocking wrong. The APIs of MuteXT. As an example of how to use Mutex, let's start by using Mutex in a single-threaded context as shown in listing 16-12. Listing 16-12, exploring the APIs of MuteXT in a single-thread context for simplicity. As with many types, we create a MuteXT using the associated function new. To access the data inside the mutex, we use the lock method to acquire the lock. We call, this call will block the current thread so it can't do any work until our turn to have the lock. So the call to lock would fail if another thread holding the lock panicked. In this case, no one would ever be able to get the lock, so we've chosen to unwrap and have this thread panic if we're in that situation. After we've acquired the lock, we can treat the return value named num in this case as a mutable reference to the data inside. The type system ensures that we acquire the a lock before using the value in m:mutex I32 is in I32. So we must acquire the lock to be able to use the I32 value. We can't forget the type system won't let us access the inner I32 otherwise. As you might suspect, MuteXT is a smart pointer. More accurately, the call to lock returns a smart pointer called MutexGuard, wrapped in a lock result that we handled with the call to unwrap. The MutexGuard smart pointer implements defer to point at our inner data. The smart pointer also has a drop implementation that releases the lock automatically when the mutex guard goes out of scope, which happens at the end of the inner scope in listing 16-12. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads because the lock release happens automatically. After dropping the lock, we can print the mutex value and see that we're able to change the inner I32 to 6. Sharing a mutex T between multiple threads. Now let's try to share a value between multiple threads using mutex T. Let's see, we'll spin up 10 threads and have them each increment a counter value by 1. So the counter goes from 0 to 10. The next example in the listing 16-13 will have a compile time error, and we'll use that error to learn more about using mutex T and how Rust helps us use it correctly. Listing 16-13, 10 threads, each increment a counter guarded by mutex T. We create a counter variable to hold an I32 inside a mutex T, as we did in listing 16-12. Next, we create 10 threads by iterating over the range of numbers. We use thread : spawn and give all the threads the same closure. One that moves the counter into the thread acquires a lock on the mutex T by calling the lock method, and then adds 1 to the value of mutex. When a thread finishes running its closure, num will go out of scope and release the lock so another thread can acquire it. In the main thread, we collect all the join handles. Then, as we did in listing 16-2, we call join on each handle to make sure all the threads finish. At this point, the main thread will acquire the lock and print the result of the program. We hinted that this example wouldn't compile. Now let's find out why. The error message states that the counter value was moved in the previous iteration of the loop. So Rust is telling us we can't move the ownership of lock counter to multiple threads. Let's fix the compiler error with the multiple ownership method we discussed in Chapter 15. Multiple ownership with multiple threads. In Chapter 15, we gave a value multiple owners by using the smart pointer RCT to create a reference counted value. Let's do the same here and see what happens. We'll wrap the mutex T in a RCT in listing 16-14 and clone the RCT before moving ownership to the thread. Now that we've seen the errors, we'll also switch back to using the for loop, and we'll keep the move keyword with the closure. Listing 16-14, attempting to use RCT to allow multiple threads to own the mutex T. Once again, we compile and get different errors. The compiler is teaching us a lot. Wow, that error message is very wordy. Here's the important part to focus on. RC mutex I32 cannot be sent between threads safely. The compiler is also telling us the reason why. The trait send is not implemented for RC mutex I32. We'll talk about send in the next section. It's one of the traits that ensures the type we used with threads are meant for use in concurrent situations. Unfortunately, RCT is not safe to share across threads. When RCT manages the reference count, it adds the count for each call to clone and subtracts from the count when each clone is dropped. But it doesn't use any concurrency primitives to make sure that it changes to the count can't be interrupted by another thread. This could lead to wrong counts, subtle bugs that could in turn lead to memory leaks or a value being dropped before we're done with it. Well, let's see, what we need is a type exactly like RCT, but one that makes changes to the reference count in a thread safe way. Atomic reference counting with ARCT. Uh, Fortunately, ARCT is a type like RCT that is safe to use in concurrent situations. The A stands for atomic, meaning it's an automatically reference counted type. Automatics, atomic, atomic, okay, Minics are an additional kind of concurrency primitive that we won't cover in detail here. See the standard library documentation for standard library sync atomic for more details. At this point, you just need to know that atomics work like primitive types but are safe to share across threads. You might then wonder why all primitive types aren't atomic and why standard library types aren't implemented to use ARCT by default. The reason is that thread safety comes with a performance penalty that you only want to pay when you really need to. If you're just performing operations on values within a single thread, your code can run faster if it doesn't have to enforce the guarantees automatics provide. Let's return to our example ARCT and RCT have the same API, so we fix our program by changing the use line, the call to new, and the call to clone. The code in listing 16-15 will definitely compile and run. Listing 16-15 using an ARCT to wrap the Mutex T to be able to share ownership across multiple threads. This code will print the following. We did it. We counted from 0 to 10, which may not seem very impressive, but it did teach us a lot about Mutex T and thread safety. You could also use the program structure to do more complicated operations than just incrementing a counter. Using this strategy, you can divide calculation into independent parts, split those parts across threads, and then use a Mutex T to have each thread update the final result with this part. Okay, similarities between reference cell T and RCT and Mutex T and ARCT. You might have noticed that the counter is immutable, but we could get a mutable reference to the value inside it. This means MuteXT provides interior mutability, as the cell family does. in the same way as we used reference cell T in Chapter 15 to allow us to mutate contents inside an RCT. We use the Mutex T to mutate contents inside an ARCT. Another detail to note is that Rust can't protect you from all kinds of logic errors when you use Mutex T. Recall in Chapter 15 that using RCT came with the risk of creating reference cycles, where two RCT values refer to each other, causing memory leaks. Similarly, Mutex T comes with the risk of creating deadlocks. These occur when an operation needs to lock two resources and two threads have each acquired one of the locks, causing them to wait for each other forever. If you're interested in deadlocks, try creating a Rust program that has a deadlock. Then research deadlocks, mitigating strategies for mutexes in any language, and have a go at implementing them in Rust. The standard library API documentation for Mutex-T and Mutex Guard offers useful information. We'll round out this chapter by talking about the send and sync traits and how we can use them with custom types. Extendable concurrency with sync and send traits. Interestingly, the Rust language has very few concurrency features. Most every concurrency feature we've talked about so far in this chapter has been part of the standard library, not the language. Your options for handling concurrency are not limited to the language or the standard library. You can write your own concurrency features or use those written by others. However, two concurrency concepts are embedded in the language: the standard library : marker trait and sync and send, allowing transference of ownership between threads with send. The send maker trait indicates that ownership of the type implementing send can be transferred between threads. Almost every Rust type is send, but there are some exceptions, including RCT. This cannot be send because if you cloned an RCT value and tried to transfer ownership, the clone to another, transfer ownership of the clone to another thread, both threads might update the reference count at the same time. For this reason, RCT is implemented for use in single thread situations where you don't want to pay the thread safety performance penalty. Therefore, Rust type system and trait bounds ensure that you can never accidentally send an RCT value across threads unsafely. When we tried to do this in listing 16-14, we get an error. The trait send is not implemented for RC Mutex I32. When we switch to ARCT, which is send, the code compiled. Any type composed entirely of send types is automatically marked as send as well. Almost all primitive types are send, aside from raw pointers, which we'll discuss in Chapter 19. Allowing access from multiple threads with sync. The sync marker trait indicates that it is safe for the type implementing sync to be referenced from multiple threads. In other words, any type T is sync if reference T, a reference to T, is send, meaning the reference can be sent safely to another thread. Similar to send, primitive types are sync, and types composed entirely of types that are sync are also sync. The smart pointer RCT is also not sync for the same reason that it's not send. The reference cell T type, which we talked about in chapter 15, and the family of the related cell T types are not sync. The implementation of borrow checking that reference cell T does at runtime is not thread safe. The smart pointer Mutex T is sync and can be used to share access with multiple threads, as you saw in the sharing a mutex T between multiple threads section. Implementing send and sync manually is unsafe. Because types are made up of send and sync traits are automatically send and sync. We don't have to implement those traits manually as marker traits. They don't even have any methods to implement. They're just useful for enforcing invariants related to concurrency. Manually implementing these traits involves implementing unsafe Rust code. We'll talk about using unsafe Rust code in Chapter 19. For now, the important information is that building new concurrent types not made up of the send and sync parts requires careful thought to uphold the safety guarantees. The Rust Nomicon has more information about these guarantees and how to uphold them. Summary. This isn't the last you'll see of concurrency in this book. The project in chapter 20 will use the concepts in this chapter in a more realistic situation than the smaller examples we discussed here. As mentioned earlier, because very little of how Rust handles concurrency is part of the language, many concurrency solutions are implemented as crates. These evolve more quickly than the standard library, so be sure to search online for the current state-of-the-art crates to use in multi-thread situations. The Rust standard library provides channels for message passing and smart pointer types such as MuteXT and ARCT that are safe to use in concurrent contexts. The type system and the borrow checker ensure that the code using these solutions won't end up with data races or invalid references. Once you get your code to compile, you can rest assured that it will happily run on multiple threads without the kinds of hard to track down bugs common in other languages. Concurrent programming is no longer a concept to be afraid of. Go forth and make your program concurrent fearlessly. Next, we'll talk about idiomatic ways to model problems and structure solutions as your Rust programs get bigger. In addition, we'll discuss how Rust idioms relate to those you might be familiar with from object-oriented programming.